Welcome to another day of thermochemistry. Today we're looking at this phase change diagram. Let's label it pressure and temperature. These are our two main variables. To get the different phases, we have liquid, gas, and solid. In between each of these is a different process. For example, we have condensation and evaporation, deposition and sublimation, and freezing and melting. Here in the middle, as you notice, we have this purple point, which we call our triple point. This is where all three exist in equilibrium, making it easy to change from one to another and back again. Notice that when we have a higher pressure, it also means that we have to have a higher temperature to change from, say, a solid to a gas or a solid to a liquid. So, higher pressure means higher temperature. This is shown by the critical point, where actually the pressure is so high that there is no temperature that can make a solid to a gas or a liquid to a gas any longer. Thank you for learning with me today. See you in my next video.
Hi, this is a day in the life of an LT chemistry student. So the first thing that I do in the morning is I make my bed, and oh my goodness, I'm so sorry. Those are my notes from last night from chemistry. I'm telling you, when you learn about the specific heat capacity formula, which is Q equals to MC change in T, and you learn that Q is the heat energy of the substance, M is the mass of the substance, and C is the heat capacity of the substance, and triangle T is the change in temperature that occurs, your life is changed. The next thing I do in the morning is I brush my hair, make sure that I'm all presentable, and I go to school. When fourth period comes along at school, I'm in chemistry and we're doing specific heat capacity questions. Until today, I'm doing a 500 gram cube of lead is heated from 25 degrees Celsius to 75 degrees Celsius. How much energy was required to heat the lead? The specific heat of lead is 0.129 joules per gram Celsius. And so I write down all the values that I know onto the side, and then I plug in all the values that I know into the problem, and make sure that you minus your two different temperatures that the problem gives you. And so I got 50 degrees Celsius from that. And so after you put in all your numbers for your variables, you type all that into the calculator. And today my answer that I got was 3,225 joules. I come home from school and I get to study chemistry. Yay, favorite part of the day. And I finally memorized that the specific heat capacity is the amount of heat energy needed to raise a gram of a substance by 1 degree Celsius. Next, I go outside to see my fur babies. I love telling my dogs what I learned, and today I told them that our house was made out of bricks because they have a high specific heat capacity, making them able to absorb all the hot Texas heat that we get, keeping our house cool on the inside. Then I go inside to cook myself some dinner on a cast iron skillet, which has a high specific heat capacity, making it able to retain heat well and cook food thoroughly. I spend the rest of my night relaxing and watching TV. Bye!
Hello guys, today we're looking at this exothermic reaction. Let's draw our graph. On the side, we have our potential energy. And on the bottom, we have our reaction progress. Let's draw our line. This is an exothermic reaction. We got our reactants and we got our products. Now we're going to draw our activation energy. As you can see, this activation energy is quite small, while this energy being released is quite large. So there's our activation energy, which is the energy it takes to start the reaction, and our energy, which is released. This is a characteristic of an exothermic reaction. So it starts with a high potential energy and also has a low activation energy. So it requires a low activation energy. And this ends with a lot of energy released, which means that it has a lower level of energy than it does at the beginning. Now we're going to look at this endothermic reaction. Let's draw our graph. We have our potential energy, and we have our reaction progress. This time our line looks a little bit different. We still have our reactants in the product, but this time the activation energy is way higher, and our energy is absorbed instead of released. It's also much smaller. So our activation energy, the requirement for the activation of the process is much larger, meaning it takes more energy, and the energy absorbed is also quite large. So it starts with a low potential energy, requires a high activation energy, and ends with much higher energy than in the beginning, due to the energy absorbed. See you next time!
Get ready with me while I talk about my ex. Let's call him Ted. So it was our 2-week anniversary, and I thought that Ted was going to take me to the restaurant I've been talking about all week. But no, all he decides to do is bring me flowers. Who does that? So I told him, I was like, you could use kinetic energy, which is the energy of motion, which powers moving objects, to go take me to the restaurant I wanted to go to all week. But no, you sat on the couch like a big couch potato full of potential energy, which is stored energy, and stayed there motionless. And you literally sat there like a runner on a starting block before a race, full of potential energy, and did nothing. Can you guys believe him? He literally sat there like a bow and arrow pulled back and not yet released, full of potential energy, and did nothing. He literally could have been like an Olympic track runner in the 100-meter race, sprinting to go out with me. Or like a baseball player running towards home base, and they're both full of kinetic energy. And what? He did nothing. Also, he broke the law. The law of conservation of energy that clearly states that energy can neither be created nor destroyed, only converted from one form of energy to another. And doesn't that imply that he should have converted his potential energy into kinetic energy to go to that restaurant with me? But instead, he used the kinetic energy in his car to hit my parked car, which had potential energy, and therefore he put his kinetic energy into my car, and now my car had kinetic energy and ran into my garage. He's gonna be hearing from my lawyer. Anyway, I love you all. Kisses.
Hello class, and welcome to Thermochemistry 101. Today we're looking at this graph. As you can see, we have temperature and we have our heat added. And we have this funky little line that we're going to explore into more depth. This first section, the temperature is increasing and the material is solid. This second section, the temperature is constant and the material melts. In the third section, temperature is increasing and the material stays in the liquid state. In the next section, the temperature is constant and vaporization occurs, so the material turns to a gas. In the last section, the temperature is increasing and it stays a gas. After looking at all of this, we can conclude that when phase changes happen, the heat added increases while the temperature stays constant. Keep learning thermochemistry. See you in my next video.
Hello everyone, and today we're back with ASMR Chemistry Edition. Today we'll be diving into the exothermic and endothermic reactions of our world and the calming sounds that are produced from them. Let's dive into our experience, shall we? Before we listen to the beautiful sounds, we must know what an exothermic and an endothermic reaction are. First, exothermic reactions are reactions that release energy. Most of the time, that energy is heat. Exothermic reactions start with a lot of energy, but lose it in the end because of the energy that was released during the reaction. Here are two examples of these sounds. The burning candle is an example
reaction to gain energy. Here are some examples. The egg is absorbing heat from the gas stove, causing the proteins inside of it to denature, making the egg cooked and edible. The water molecules absorb the energy from the gas stove, causing them to phase change into gas. And that is another example of an endothermic reaction. Thank you for